Hello, so today we're going to look at the natural log, but let's go ahead and review some properties with logs. Recall that the log base b is actually x is equal to the base to the exponent y. Base is positive, not equal to 1, domain is positive numbers, range is all real numbers. If the base is not given, we can assume it's base 10. And then we write base e, our natural log, as ln of x. And here's just a reminder, e is approximately 2.72. So an interesting definition of our natural log is also the following. The natural log of x is equal to this integral here of 1 over, in this case we have to use variable t because x is already in use. Okay, so recall from Calc 1, if we had an integral of the form 1 over x. To evaluate that, we would write it as x to the negative 1, and then we add 1 to the exponent, so we get x to the 0, and divide by 0, which is undefined. So in Calc 1, we could not evaluate integrals of this form, but now in Calc 2, we can. That integral is just the natural log of x. So let's go ahead and review some properties. We already talked about number 1, the domain and range, right? It's going to be positive numbers for domain, all real numbers for the range. So this property 2 says that if you have a product in the argument, you can separate it into 2 logs with addition. And if you have a division in property 3, you can separate it into 2 logs with subtraction. Property 4 says if you have an exponent p on an argument, you can bring it out in front. So what's new is 5, 6, and 7. Okay, so property 5 is the derivative of a natural log. The derivative of the natural log is just 1 over the argument. But we can also use the chain rule. In property 6, the derivative of the natural log of a function of x would be 1 over the argument times the derivative of the argument. And then we already talked about 7. If we're looking at the integral of 1 over x, it's going to be the natural log of, and we need the absolute values here, the absolute value of x. So let's go ahead and work on some examples. Let's look at A. If I was going to find the derivative, first thing I want to note is that this is a product of 2 functions of x. So I have to use the product rule. And now notice in the natural log, there's no absolute values around 3x, and that's okay. If there's no absolute values, you can just assume it's defined for x greater than 0 in this case. So when I take my derivative, it's going to be derivative of x, which is 1. The natural log of 3x stays, plus x, times the derivative of the natural log of 3x, which is going to be 1 over the argument. Notice I don't have the absolute values anymore, times the derivative of the argument. If we clean that up, we have the derivative is natural log of 3x plus 1. And that's it. Okay, so moving on to another example, example B. Note in example B, we do have absolute values around the argument, okay, which is fine. Again, if they weren't there, that would be fine too. We just assume it's defined for the x value, so that cosine is always positive. So when I take the derivative, it's going to be 1 over the argument, which is cosine of 2x, times the derivative of the argument. Here I think I'm going to write it out. It's a little bit more difficult for me to see what the derivative is because of the repeated use of the chain rule. So I'm going to take the derivative of cosine of 2x. And the derivative of cosine of 2x is negative sine of 2x, again we have to use the chain rule, times the derivative of the argument 2x. And in that case, that would be 2. So if we put this all together, the derivative is negative 2 sine of 2x over cosine of 2x. Okay. I left off the parentheses on the argument because it's clear that the whole thing 2x is the argument, or you can leave it on. Okay. And then I can write that in a simpler form as 2 tangent of 2x. Okay, so we're done with that example. Let's go to the next page. And I'm going to zoom this in. Okay, so in example C is kind of a mess. Because if I take the derivative, it's 1 over that argument times the derivative of that argument, which would involve the chain rule and the quotient rule, and I think that's it. Oh, maybe the product rule. I don't want to do all that. What I'm going to do first is use my properties of natural log to separate this into the natural log of x plus 1 minus the natural log of x cubed minus 3. So now it's just a process of finding the derivative for each of those pieces separately. It's a lot simpler. So the derivative is going to be on the first piece, 1 over the argument, times the derivative of x plus 1, which is just 1, minus 1 over the argument, times the derivative of the argument, which would be 3x squared. I'm going to clean this up to write 1 over x plus 1 minus 3x squared over x cubed minus 3. And here is where you can stop. It's not necessary for you to do that subtraction and bring those two fractions together. Right? So much nicer using log properties first. Okay, let's do some integrals. So in example 3a, I have a problem again, because what I have is division of two functions of x, which I'm not allowed to do. So what I'm going to do first is a substitution. I'm going to let u equal the denominator x squared minus 4, because I notice when I take the derivative with respect to x, it's going to be 2x, and perhaps the x in the numerator of my integrand will cancel. Okay. So in other words, dx is equal to du over 2x. But I also want to change my limits of integration. So if x is equal to 1, then u is going to equal negative 3. And if x is equal to 0, then u is going to equal negative 4. So now the integral is going to be from negative 3 to negative 4 of x over u times du over 2x. So now notice that the x's will cancel. And here I think I'm going to bring this 1/2 out in front. So I have 1/2 integral of negative 3 to negative 4 of 1 over u du. And that would be our natural log. So we have 1/2 times the natural log of the absolute value of u, and we're going to evaluate this from negative 3 to negative 4, which is 1/2. I think I'm going to keep this 1/2 on the outside and evaluate natural log absolute value of negative 3 minus natural log absolute value of negative 4. Okay, I need more space. So the absolute value of negative 3 is just 3. Absolute value of negative 4 is just 4. So this is going to be 1/2 times the natural log of 3 minus the natural log of 4. And then I can simplify this further, because the natural log of 3 minus the natural log of 4 is just the natural log of 3/4 by our property. And I can simplify this even further, because this 1/2 in the front can be brought up to be the exponent on 3/4. So I'm going to have the natural log of 3/4 to the 1/2 power, and if you remember, the 1/2 power is just the square root. So we have the natural log of the square root of 3/2. Okay, so this is much nicer than stopping here. So this is where I would stop. Okay, let's do another example. I have the integral of the natural log of x over 2x. Again, I have a quotient or division of two functions of x, so I cannot integrate it the way it is. I'm going to do u substitution. I'm going to let u be the natural log of x, and that's because I know the derivative is going to be 1 over x. So hopefully something will cancel inside that integral. Okay, so this is natural log of x dx. No, that won't work. Sorry, my mistake. I think dx equal to x du. I apologize. So now my dx is going to be the x times du, and I can see the x's will cancel. So this will be the integral of u over 2x times x du. My x's cancel. I'm going to pull out the 1/2, and I'll have the integral of u du, which is super nice because that's just u squared over 2. Okay, plus my constant c, since it's an indefinite integral. Okay, but now I have to substitute back in for u the natural log of x. So it's going to be the natural log of x quantity squared over 4 plus c. Here I'm getting sloppy with my no equal signs. But like our trig functions, we can rewrite the natural log of x quantity squared as the natural log squared of x. And that way we don't need the parentheses. So this actually looks much nicer. And this is where I would stop. Okay, the next thing I want to do is I want to go ahead and look at the function of the natural log of x. And I want to talk about finding its inverse. Now this is going to bother me to no end, not having arrows at the end of my function, but this is my function f. So there's a few points here on f. This would be the point 1, 0, and here, when y is 1, this is actually e. So if I was going to find the inverse function for the natural log, which you should notice from the graph is a 1-to-1 function, I would replace f of x with y. I don't want to exchange the x's and the y's yet, right? Because the goal is to solve for x first. Unfortunately, x is in the argument of natural log, so in order to solve for x, what I need to do is switch this to its exponential form. And once I've done that, this is solved for x, I can go ahead and exchange my x's and my y's and replace y with the inverse function notation. Oops, sorry. So it turns out that the inverse function of the natural log is the exponential function e to the x. And if we were to graph that, I'll use a different color. If f goes through 1, 0, e to the x goes through 0, 1. If f goes through e, comma 1, we have 1 comma e, which would probably be around here. So the inverse function goes up, and then it's going to come down and follow the x-axis. Okay, so e to the x is the inverse of the natural log of x. So let's look at some properties of our exponential function. Sometimes you may see y equal to e to the x written as y equal to exp of x, which just means exponential function. They mean the same thing. So let's review some properties. Property 1, whenever you have a base, and in our case it's base e, and you're adding exponents, you can break it up into a product of e to the x times e to the y. Subtraction turns into division. If you take e to the x and raise it to the power of y, you can just go ahead and get rid of the parentheses and multiply the exponents. Okay? So this is a property that we use quite often. The natural log of e to the x is just x, because natural log of e is 1, so it kind of cancels. And then if you take e to the ln of x, that is x as well. So something you may not have seen is property 6. Okay? If you take any base, not just e, any base, raise it to the x power, it can be rewritten as e to the x times natural log of the base. So let's just this is fun. Let's go ahead and review how we would solve some equations with logs and exponential functions. Okay. So part A, there's a lot of ways that you can solve this equation. I'm going to choose to do it the following way, just so we can practice using our properties. What I'm going to do is I'm going to erase that and change the color of my pen. I am going to put all my logs on one side. So I'm going to subtract the natural log of y plus 5 from both sides, and I'm going to add x to both sides. So I get all my logs on one side, everything without a log on the other side. And then I'm going to use my log properties to write this as a natural log of sine of x over y plus 5. Okay, so now this is an equation. I'm allowed to take this to the power of e on both sides. And when I do that, by a previous property, e to the ln would cancel, and what I'm left with is sine of x over y plus 5 equal e to the x. So now it's just a matter of algebra. So in the beginning, the problem with solving for y was it was in the argument of the natural log, and we had to try to figure out a way to get it out. So now we have y plus 5 is equal to sine of x over e to the x. And if we subtract 5 from both sides, we are done. And I've solved this for y. I do not require you to combine those, but you can if you wish. So let's look at another example. So instead of having logs, we have the exponential function. Again, solving for y is an issue because y is in the exponent, so I need to get it out. So what I'm going to do is I'm just going to take the natural log on both sides. Again, we are allowed to do the same thing on each side of an equation. So when I take the natural log on both sides, hopefully you can see that here the natural log of e will cancel. So I have y plus x is equal to the natural log of 5x squared. And then I just have to subtract x from both sides. I'm going to put the minus x in the front so there's no confusion about what the argument of the log is. But it's not necessary. You could have done it on the other side. And that's it. We've solved for y. All right. So now let's look at taking the derivative of our exponential function. And e to the x is probably one of the nicest functions we'll come across. And the reason why is because when we take the derivative, it remains unchanged. The derivative of e to the x is e to the x. Using the chain rule, the derivative of e to a function of x is equal to, stays the same, times derivative of the exponent. So look at the integral as well. That remains unchanged. If we integrate e to the x, it's e to the x. So super nice. Let's do an example. If we take the derivative of 4 times e to the sine of x plus e to the negative x, that derivative is, equal to 4 e stays the same times the derivative of the exponent, which is cosine of x, plus e stays the same times the derivative of the exponent, which is -1. So just cleaning this up, and sorry, this is my pet thing. I like the cosine in front of e. To me, it just looks better. And then this would be a minus e to the negative x. All right, so if the directions say that you have to answer with positive exponents, then you can go ahead and flip it. Again, I don't require that. You're done. Okay, so let's look at part B. This time we're asked to find a derivative and evaluate it when x is equal to 2. So if you look at the argument, 3 times x times e to the -3x, I really don't feel like taking the derivative of 1 over the argument and then multiplying it by the derivative of that argument, because that involves the product rule. These are products of functions of x. So instead I'm going to use my properties like I did before, and I'm going to expand this out to be the natural log of 3 plus the natural log of x plus the natural log of e to the -3x. And that would be evaluated for x is equal to 2. So simplifying, this is the natural log of 3 plus the natural log of x minus 3x. Right? Because of our property. So when we take the derivative here of the natural log of 3, remember that's just a constant number. There's no variable there. So the derivative of a constant is 0. So this is going to be 0, right? This is just 0. Derivative of natural log of x is 1 over x. Derivative of minus 3x is just 3. So we're evaluating this for x is equal to 2. And that's going to be 1/2 minus 3, which is -5 over 2. Sorry. Do simple math in my head. It's kind of frightening. All right. Let's go on to some more examples. This time we're going to be looking at integrals. So again, let me zoom this in. If I want to evaluate example 6a, I have a quotient of 2 functions, so I can't integrate the way it is. So again, I'm going to do my go-to u substitution. So I'm going to let u equal the denominator 1 minus e to the x. And then the derivative with respect to x is going to be just negative e to the x. Okay? So what you could note is that negative du is equal to e to the x dx, which is this top piece of my integral. So now my integral is going to be equal to the integral of, this is just negative du over u. Okay, so this is going to be the negative integral of du over u, or 1 over u times du, which is negative natural log absolute value of u plus c. And when substituting back for 1 minus e to the x in place of u, I just have to do a final check to make sure that this is simplified. Oftentimes, inside the absolute value, you'll be able to simplify. Doesn't look like it. It looks like I can just stop here. So let's move on to another example. Let's look at example B. Example B, we have a few issues here. So one thing that's going on is that I have a 6 that I could pull out. Okay. The other issue is that e to the 3x is in the denominator, so I want to bring it up. So it's e to the negative 3x, because I'm trying to make this look like e to the something, so I can integrate. Another issue I have is the minus 3x. It's not just x, it's negative 3x. So in this case, we're going to have to do a u substitution on the exponent, and we're going to let u equal negative 3x. So the derivative with respect to x is just negative 3. Or in other words, dx is equal to negative du over 3. I can also look at changing my limits of integration. If x is equal to 2, then u is going to equal negative 6. If x is equal to 0, then u is equal to 0. So now my integral is going to be 6 times the integral of negative 6 to 0. And it's okay if your upper limit is less than your lower limit. E to the u times negative du over 3. So if we take out that negative 1/3, we get a negative 2 integral from negative 6 to 0 of e to the u du. And that I know how to integrate. Now if you choose, you can go ahead and get rid of the negative in front of the 2 and swap your limits of integration, but I'm not even going to bother. Okay? I know that the antiderivative of e to the u is just e to the u. So it's negative 2 e to the u evaluated from negative 6 to 0. So negative 2 e to the negative 6, maybe I'll deal with the negative 2 later, minus e to the 0. Negative 2 e to the negative 6 minus 1. I don't like all those negatives. Maybe I'll switch this order around, right? And write this as 2, 1 minus e to the negative 6. I think that looks prettier. And I'm going to stop here. You could have actually stopped here. I just thought it looked weird. All right, oops, I apologize. Let's not go to the next page. Let's continue on with the rest of the examples on this page. So for example 7, we have to find the equation of a tangent line to the graph at a given point. So whenever we find the equation of a line, we're going to use y minus y sub 1 is equal to mx minus x sub 1. So we need our m and we need our point. Well, we have our point, right? Our x sub 1, y sub 1 is 0, negative 3. So the only thing I need is my slope. Okay? And my slope is the derivative. It's going to be the derivative evaluated for the x value of 0. So let's go ahead and compute the derivative of this equation. The derivative is 1 minus 3, e stays the same, times the derivative of the argument, so 1 minus 6 e to the 2x. So when I evaluate for x equal to 0, which is my slope, I get 1 minus 6 times e to the 0, which is 1, so that's gone, and it's negative 5. So the equation of the tangent line is going to be y minus a negative 3 or plus 3 equal to negative 5, x minus 0, so it's just x. So typically we want to write our equations in slope-intercept form, so I would minus the 3 from both sides. So this is the equation of the line, tangent to the function at the point 0, negative 3. Okay, and just recall, did we call this the slope-intercept form? So if your directions are to write the final answer in slope-intercept form, just solve it. Go to the next page. This is probably one of my favorite examples. It's the process of logarithmic differentiation. So if I was to compute the derivative here, it would be a complete mess. Because this function, when I find the derivative, involves the quotient rule and the product rule and the chain rule. So instead, what I'm going to do is I'm going to use logarithmic differentiation, which means I am going to take the natural log on both sides, but I really don't like all this notation. So I'm going to replace f of x with y. And then I'm going to take the natural log on both sides. What that will allow me to do is use my log properties to separate this argument into smaller pieces so that it's easier to take the derivative. So what I'm going to attempt to do is expand this out all the way. So this is going to be the natural log. Everything on the top is plus. So natural log of x squared plus 3 plus the natural log of, and I don't like square roots, I'm going to write this as 2x plus 1 to the 1/2 power. The denominator is going to be the minus natural log of x squared minus 5 to the 3rd power. So now that I have it expanded out, I'm also going to do a little bit more work. And I'm going to use this log property to take our exponents out into the front, the 1/2 and the 3. So we have 1/2 times the natural log of 2x plus 1 minus 3 times the natural log of x squared minus 5. Okay. So remember, this is all equal to the natural log of y. I don't want to forget that. When I take the derivative at this point, I have to take the derivative on both sides. The problem is here you have to remember natural log of y. Y is a function. So we have to use implicit differentiation. If I take the derivative, it's 1 over y times the dy dx equal to, and then when we take the derivative of natural log of x squared plus 3, it's going to be 1 over x squared plus 3 times the derivative of the argument, which would just be 2x, plus 1/2 times 1 over the argument, times the derivative of the argument, which is 2, minus 3 times 1 over the argument, times the derivative of the argument, which would be 2x. So let's just go ahead and clean this up a little bit. And let me move this up just a scotch. Okay, so we have 1 over y times dy dx is equal to 2x over x squared plus 3 plus, and here this is nice, the 1/2 and the 2 will cancel, so we just have 1 over 2x plus 1 minus 6x over x squared minus 5. So this was a lot easier than taking the derivative from the beginning. The problem is, notice that this is not just the derivative. We have this 1 over y. So we have a few more steps. First thing we want to do is get the derivative by itself by multiplying both sides of this equation by y. So it's y times all of this. But then we have the derivative is supposed to be with respect to x. But we have this y here. So we need to replace that y with the original value of our function, which would be the x squared plus 3 times the square root of 2x plus 1 divided by x squared minus 5 cubed. And then all of this is going to be times the 2x over x squared plus 3, sorry. So it looks pretty awful, but this is it. You're done. And you could stop here. And that's it. Okay, so that's it for this lecture.